So let's talk here briefly about some conventions for writing nuclear transmutations or nuclear decays. This sort of a shorthand way of writing these is a little bit more convenient than writing out the full reactions. So if we look at the changes that occur when a nucleus such as nitrogen-14 is bombarded with a particle such as the alpha particle, and that will form oxygen-17 and a proton. We can write that in shorthand. So we would write the target nucleus, which that's what's being struck by the smaller particle, or maybe even gamma radiation. And then in parentheses, we would put the bombarding particle, and then an ejected particle, followed by a product nucleus. So the things that go on the outside, that are outside of the parentheses, are the larger nuclei before and after reaction. And then inside the parentheses are going to be bombarding particles and particles that are ejected. So you may see this come up, you will see this come up in your homework. I wanted you all to be aware of that. Okay. One of the cool things that involves nuclear chemistry that we take advantage of are particle accelerators. So these are going to be really large facilities where we'll take particles that have high energy and are moving very quickly, almost the speed of light, and we'll smash those particles together. Okay? There's a number of these facilities all over the world. Fermilab, that's the picture that's shown here. CERN, you probably heard of the CERN super collider, Large Hadron Collider. But so what in this picture here, we have these circles. These are the particle accelerators. So what you do is you form a charged particle, which we can then move throughout these tunnels, very large circumference tunnels, by way of either an electric or magnetic field, get them moving nearly the speed of light, and then collide them together and watch the reactions that take place. And so I have let me see what my next slide is. Yeah. This is one of the ways that we've used to produce elements with a mass larger than uranium, so the transuranium elements. This is also the way we've produced new elements in the last few years with these particle accelerators. So I have some fun videos I wanted to watch. It's cool to see what these actually look like. Let's see here. I gotta remember how to do this. Okay. There we go.
This beautiful piece of human ingenuity, engineering, and wait a minute, that's not the LHC. This is the LHC.
That's really nice.
This is the Large Hadron Collider, or LHC for short. It's a 27-kilometer particle accelerator sitting under the border of France and Switzerland. It's an atom smasher, the biggest in the world, designed and built by thousands of engineers, scientists, and mathematicians.
Hang on, I can't. That's too loud to even hear. I can't. I just can't handle that. I have no idea how to turn the volume down right now. Okay. The volume does not appear to be working on this. that the element tennessine was synthesized. So this paper came out in 2010. It's not the newest element that's been synthesized. The newest element that's been synthesized is organocin, and it's based off actually the name of the first author here in this paper. The element was named after him, the newest element. But in any case, so producing element 117. Let me see where we're. Let me make sure I spell it right. Tennessine. So named after the state of Tennessee. A lot of the researchers who were working on this element were based in Oak Ridge National Lab, where there is a large particle collider, and that is based in Tennessee. So that's where that comes about. But as mentioned in that video, these elements don't last very long. They have a really short half-life, which we'll talk about here briefly. So when they made these new elements, what they did was they found two isotopes that had relatively long half-lives. So one of them was about 45 milliseconds, and the other was about 10 milliseconds, between 10 and 21. And so those are, it's not long at all. Okay, they don't last for even a second. That's why these new elements, they're not stable. And in the video, they mentioned finding an island of stability for new elements. They were expecting that elements with atomic number 120 through 126 might be stable for longer amounts of time. But so what happens then is these elements decay through, let's see. Here we go. Alpha decay. So you can see there's an alpha here. That's representing the first decay is an alpha decay. Most of these are alpha decays. And so our first isotope is tennessine 294. Okay, so there's our mass number, atomic number 117. It's going to decay to form element 115, which is also relatively new, probably. Is it on our list? Nope. We do not have it on our wall. That's how new it is. It's moscovium, abbreviated MC. Moscovium 290. It's element 115, and the decay is by alpha decay, so here's our alpha particle. And so you could figure out all of the elements that were formed in this decay chain based on what they've given in this chart. So this is from that paper on the previous slide. The other cool thing about when they discovered tennessine is that, and the reason why it's named after Tennessee is that Oak Ridge National Lab made 22 milligrams of berkelium, which is berkelium-249, which has another relatively short half-life of 327 days. And they had to ship this to Russia in order to do experiments there. So as soon as they made berkelium, they were against the clock in order to form the new element. And then what they did in the forming process was they took berkelium, BK249, and that's element 97, and they collided that with calcium 48 to form the tennessine 297, which is an isotope that they couldn't measure the lifetime of. Yes?
How did they decide which two elements are necessarily the best for?
Yeah, I actually don't, I'm not really sure on that. Of course, you need to have the mass numbers and atomic numbers add up to where you want to be. Stability is going to be an issue of the isotopes, and then with the calcium, this is probably chosen also because it's cheap, and so you can get a large mass of it and just blast the berkelium. Yeah. Does anyone have a guess on how many atoms they made of tennessine?
4.
Close.
5.
Closer.
6.
Yes, they made 6 atoms. That's how many have been made so far. That's crazy to me.
Do you have any idea how they are able to count how many atoms they've made?
Yeah, so each decay process is triggered on a detector, and so they have 6 different triggers, and they're called occurrences. So when you read, if you were to look at the paper, it would say 6 occurrences.
How do they decide, like, at some point that, it's obviously incredibly unstable, so
Yeah.
at some point, how do you decide, oh, this isn't stable enough at the point where we can consider this a non-transition, or I guess.
How do you know it's real?
Yeah, how do you know it's an actual element versus?
Yeah, that's really challenging, and I believe it was this element that was originally discovered at Lawrence Berkeley, but the authors made up the data. So that didn't, this is the real version. Yes?
So, I'm sure you made a lot of money on this. All of it's equal to find something that's legal, that somehow
Hang on, guys. I can't hear in the back. Go ahead. One more time. Sorry.
So I was just saying, they're spending a lot of money on this, and it's all out in the hope that they'll find some other element that's going to be stable, that'll have properties different than what we already have.
Yeah, why do we spend so much money on this, I think is your question. And yeah, so I believe the goal is to make an element that'll do things that we want it to do, probably produce energy in the way we want it to do. We're going to talk about fission and nuclear energy in a little bit. But I think the goal is probably, there's got to be some sort of monetary reason, right, to make this. And the more stable isotope you have, the more chance you have to use it for something. So, yeah. It's a good question. Cool. Anything else? All right. Sorry for blasting your eardrums. Okay, so one of the really important things to consider with nuclear chemistry is the rates of decay. And so we've seen kinetics already earlier in the semester. Was that chapter 14, I believe? And so this is essentially just a review for you on some kinetics. The nice thing about radioactive decay is that the type of kinetics are really predictable. All radioisotopes are going to decay by a first order decay process here, which means that we can predict concentrations of isotopes after a certain amount of time if we know the rate constant. It's all that first order decay equations. If you recall, we'll have natural log of the concentration of a substance after some time divided by the initial concentration of that substance, and that is equal to minus the rate constant K times time. So you don't need to worry about second order decay process or third order for nuclear reactions. It will come back up soon with your final, but so this might be a good time to review those. Oops, I want to erase that real quick. The other thing, when we're going to look at a few problems here involving rates of decay, it's a good idea to remember that the half-life for a first order decay process is equal to 0.693 divided by the rate constant K. And so if you were given a problem where you don't know the rate constant, you could find that. K is going to be equal to 0.693 divided by the half-life. So hopefully that's a little bit of a review for you. Another thing to recall is what half-life means. So in this figure, we're looking at the mass of strontium-90 versus time in years. Strontium-90 has a half-life of 28.8 years. We'll see this again in a minute. And so if we start with 10 grams of strontium-90, after 28.8 years, we'll have 5 grams. And then another 28.8 years, so on and so forth. Okay. So this is a exponential decay, first order. All right. Radioactive decay rates come up in the really, I think it's kind of cool process of carbon dating, radiometric dating. Doesn't necessarily have to be carbon-based. And so it's probably the one you're more familiar with, but we use isotopes of various elements. We know their half-lives. We can predict how old something is. Two of them that work really well is carbon dating and then uranium dating. So with carbon dating, the half-life, we have carbon-14. The half-life of carbon-14 is 5,700 years. And so what happens is carbon-14 will decay by beta decay and form nitrogen-14. Okay. And so we can measure the quantity of carbon-14 in a substance, an organic substance. Typically, we're looking at plants and animal species. And the reason why that's what we're, those are the kind of limitations on carbon dating, is that if you think about what we're doing, so plants are going to use carbon dioxide from the atmosphere to produce, well, itself, use photosynthesis and make carbohydrates, excuse me. Well, that carbon-14 is consumed only when the plant is alive. Once the plant dies, it's no longer consumed. And because it has a half-life, the carbon-14 will decay and form the nitrogen-14. And so if we were to look at a ratio of carbon-14 to carbon-12, we could determine how old the substance is. One of the questions that you have might be, how is carbon-14 formed? It was formed in the atmosphere. Cosmic rays, which is a high-energy photon, collide with atoms in the atmosphere and create neutrons. Okay, so here's our cosmic rays coming in, forming a neutron. That neutron's going to react with nitrogen-14 in the atmosphere to form the carbon-14 and a proton. And then plants take up the carbon-14. Of course, animals will consume a certain level of vegetation, so we'll have carbon-14 as well. Yeah. This process of carbon dating is limited to samples that are up to 50,000 years old. After that, anything older, it's really hard to detect any measurable amount of carbon-14. Yes.
In carbon dating, if you're given, like, let's say decay and you already know the half-life of carbon, and how would using the equation of the natural log of the two masses,
Yeah.
negative kT, wouldn't there still be two variables in that equation, which is the original mass, and then as well as the time that it's been
You'll be given at this level. You'll be given enough information to know what it is.
Yeah, I'm not asking about, like, for an exam, like, for them to actually carbon date something, wouldn't they still have, like, one unknown variable, or wouldn't they need to know how much mass was originally there in order to make the equation?
Yes, that's a great question. Off the top of my head, how do they do that? So we've got a log. It's decaying. There's probably some like baseline for certain things, but I don't know for sure. Like an expected amount.
Like an approximate.
Yeah.
No, this is a tree.
And it would probably get you close
Yeah.
enough. I mean, within thousands of years, right? Yeah.
Is the half-life of decay the same with all temperature and pressure and stuff?
question. These are great questions. Okay, rate's going to be dependent on pressure. The other thing is there's a good possibility. And the other thing you can think about is now you've probably seen the plots of carbon dioxide in the atmosphere over time, thousands and thousands of years, and it is increasing. And so there are adjustments in the calculations to make for increased levels of CO2. Yeah, those are good questions. I don't exactly know all the answers. Sorry. I'm going to look into that a little bit more, because now I'm curious. We also need to know what instrument they're using to measure these things, I think. Okay, so I want to skip ahead once. So this is a radiometric dating problem. When we have non-organic substances like rocks, you can use uranium-238 as a dating isotope. Uranium-238 decays through multiple decay processes to form lead-206. And in this problem, we're given the half-life for decay for the uranium-238, and that's 4.5 times 10 to the 9 years. So here's our problem. We have a rock that contains 0.257 milligrams of lead-206. So somehow we were able to measure this for every milligram, of uranium-238. So we're going to measure mass of uranium-238, and we're going to measure the mass of lead-206. We want to know how old is the rock. With this problem, it's a little easier because now you have two things you can measure. Yeah. Okay. So one thing I want you to know is that when you're doing A at time 0 and A after some time, these have to be the same substances. So here in our problem, we were given 0.256 milligrams of lead for every 1 milligram of uranium. So we're going to have to convert those to the same species. Okay? I'm going to let you think about that for a few seconds. Okay, we're going to do a couple of things. First, and this is going to work for something you're going to have to do for other problems like this, is that assume that the only source of lead-206 is from uranium-238. Okay? That, in reality, may not be the case. There are mathematical ways to work around that that have been published in the literature, but that's not something we're going to worry about. Okay. The other thing, so our original, the way that this is worded, it's kind of hard to see where our masses might be. We're going to assume that the rock contains 1 milligram of uranium-238. And it says for every milligram of uranium-238, we've got 0.257 milligrams of lead, which means the original amount of uranium is going to be the 1 milligram plus some amount that has been transformed into the lead-206. Actually, I'll write this as formed lead-206. So we need to figure out that amount. Okay. In order to do that, let's start with our 0.257 milligrams of lead-206. And using dimensional analysis and knowing our decay process, uranium-238 forming lead-206, 1-to-1, we can figure out the original mass. So 0.257 milligrams of lead, we can convert that to grams. And I want to do that because I want to use molar mass or atomic mass units, molar mass. We're going to have 206 grams of lead for every 1 mole. Okay, that's the definition of mass number. All right, and we know that we're going to have 1 mole of lead that is formed from 1 mole of uranium. And that 1 mole of uranium-238 is 238 grams. And then, of course, converting back to milligrams. 1 gram, 10 to the minus 3, nope. Okay. Everyone see how this works? This problem is in your textbook. They approach the problem a little bit differently. They don't do this whole dimensional analysis bit. They simplify and multiply by a fraction of 238 over 206, which is essentially what you're doing here, but they don't tell you why. And this is why. You're basically using dimensional analysis to convert to a new mass. So we'll end up with 0.297 milligrams of our uranium. Okay. So the original amount, we'll call it A sub 0, of uranium is 1.297 milligrams. Everyone see that? Questions on that? So from there, we might actually pause on this one. From there, it's a matter of solving for your rate constant, plugging that in, and solving for time. How old is the rock is how long it took to go from the original concentration to the current concentration. Does that make sense? That's a tricky one. I like that one though. Yeah.
Wouldn't that also only tell you like when the organism or whatever died, not when how long it's been around?
If we were doing carbon dating, yes. But with uranium, it is the formation of that uranium. To slide 26. This example is slightly easier, so I want to start with this one. So here we have strontium 90. It's going to undergo radioactive decay to yttrium-90. First thing I want you to do, and feel free to do this in the next few seconds here, talk with your neighbor, is write the nuclear decay reaction. So go ahead and try that. All right, so for this problem, I'm going to write out my starting material, strontium 90, which has atomic number 38. And we know that it's going to form yttrium 90, which has atomic number 39. And so essentially, we're looking for the other product that's formed. And we're going to add up our mass numbers and our atomic numbers to figure that out. And what we'll end up with is, we'll see that this is a beta decay. All right. Everyone good on that? Yes?
If we were to do the short form of that, would that just mean that the left side is empty?
Yes.
Okay.
Yeah.
So you just blank column.
Yeah.
Okay.
Okay. The next thing, what is the half-life of strontium 90? That's going to be our goal. And we have some information to help us get there. And that is, if we take 0.953 grams of strontium 90, we find that that is the amount that remains in a block that originally weighed 1 gram 2 years earlier. So from that, we're going to try to figure out our half-life. So I'll let you work on that just for a few minutes. All right. So for this problem, your initial concentration, you can actually just use mass. Right? And because this is going to be a ratio. So we're going to say that our initial mass is going to be the 1 gram. And after some time, we'll have the 0.953 grams. We want to find K, our rate constant, at this step. And we know that our time is going to be 2 years. So we can plug these in. We'll have natural log of 0.953 divided by 1. Equals minus K times 2. Multiply, divide, natural log, all the stuff. And you'll get rate constant equal to 0.0241 years to the negative 1. So now we can use our equation for half-life. T1 half is equal to 0.693 divided by K. And we'll get 28.8 years. Questions on that problem? Okay, everyone comfortable with just putting in masses for a ratio? Units don't really matter. All right. Let's do the more challenging problem. Okay. We'll carry on with this. Is a good place to stop. Does anyone have any questions?
think either 2 days ago or something there was a homework due. I completely forgot about it because all the midterms. Is there any way I can make up that one homework assignment?
Yeah.
Okay.
Yeah. Did you?
I can show you it on the computer.
It's okay. If you're willing to do the work, I'm willing to give you the points.
Okay. So I just like do it and then like.
Well, I want you to write your name down so that I can reopen it for you, and I'll give you some days to do it.
Thank you so much. You need my name, down number, or just like my name?
Yes, please.
Alright, thank you.
Thank you.
Cool.
How's it going?
So I met with SLDS,
Okay.
and they said there's nothing they can really do since they said I was supposed to come talk to get accommodations for that, and
Okay.
since it wasn't like made clear they can't do anything.
Okay.
For the final, they gave me this, like a late request.
Okay.
They said talk to you if someone can like say to proctor it later for me, or if I just need to like make accommodations to go there.
Okay, so this is for me to read. Actually, do I need to fill something out?
I guess you just need to tell me what I need to do for the exam to get the accommodation.
We might need to go visit Holly again.
Okay.
Do you have time right now? Okay, let's do that then. Okay. Yes.
Hello.
How's it
I
going?
just wondered, good idea. Curve? Like, can you explain a little bit how that works?
Not really, honestly,
Okay.
because I don't quite understand it.
So I'm kind of banking off that to pass the class right now.
So the way I understand it is that the average over all of the 1220 sections is taken of like score. And then where I can't remember if it's the average is given a B minus or a C plus, but it's one of those. And I know that makes a difference, but I'm sorry, I don't remember. And then whatever number of grades are possible between there and 100%, that's divided up that many times. And then you just slot it in. Does that make sense?
That does make sense. So like people that are like farther away from the average, like me, under average, like would I be pushed up or?
I don't know. I don't think that there's ever that big of a curve, either way,
Like to be pushed up,
up
at
or
all?
down. Yeah.
I think it's always like less than 1 point, honestly.
Yeah, I
really?
don't think it's ever huge.
Okay. Because I've heard there's like 13%. I don't know. I've heard so many different things.
There's a lot of stories, and I don't know how many of them are true and how many of them aren't. And because this is my first time teaching Gen Chem, I don't have any good examples.
Yeah, of course.
either. So,
Okay.
yeah.
Thank you.
Yep.
No worries.
Sorry.
No worries.
Question about the question you were doing just then.
Yes.
So, like, what would you do after you solved for the initial?
Yeah. So then you know the mass after. You got our original mass, and then actually go back and solve for my equilibrium, my rate constant. Plugging the time in for the half-life and getting this. And then we say that our original concentration, and now it has decayed to form only 1 milligram left. Plug in K, solve for T. There's a minus sign there.
Alright, thank you.
Yep.
Also, the essential skills were reopened to me, but I only saw one of them.
Oh. I have no idea. How many do you need, do you think? Do you know? Okay, that's fine.
Yeah, okay.
All right, I'll talk with Ted. Okay. Because I don't have any power to open things. Yeah. Uh-huh. Okay. Disconnect. Nope, I'm good.